Alright, so today we're going to learn how to draw some simple covalent bonds in some simple molecules. Mr. Lewis gave us a very nice way of modeling covalent bonds. It's based upon our knowledge of valence electrons, and so we call these Lewis structures. And if we remember, the valence electrons are represented by dots around the symbol of the atom. And so here are the Lewis dot diagrams for our representative elements. And if you remember, Group 1 over here, the alkali metals, have 1 valence electron. Group 2 has 2. We skip the transition metals. And group Roman numeral 3, or modern times 13, has 3. Group 4, or group 14, has 4. And we continue on until we get to group 8, or 18, the noble gases, that have 8. And so you'll see that the valence electrons are represented as dots around the symbol of the element. Now when you have 1, 2, or 3, you just need to make sure that you have a dot on each, or one dot on a side. Once we get to group 14, like carbon here, very important, we want to have 1 dot on each side of the symbol. And carbon loves to form 4 bonds, and so you can see there that it has 4 valence electrons that it is going to want to share. Once we get to 5, 6, and 7, the next couple groups, you start doubling up. But it doesn't matter which side you double up on. Here we see that the double is on the right-hand side. You could have the double on the top or the bottom or the left-hand side. Does not matter. But so when you have 5 valence electrons, there's 3 single dots and a double dot. And those 3 single dots say, please, 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 I would like to form 3 bonds. And then we see with oxygen and its family, we have now 2 doubles and 2 singles. And then when you get to the halogens, we have 3 doubles and just 1 single valence electron that is ready, willing, and able to be shared. And a couple other notes. One, when we bond, especially now we're talking about the covalent bonds, when we share these electrons, our goal is to look like a noble gas, so that we can have 8 valence electrons and obey that octet rule. The exception, of course, our good buddy hydrogen really only needs to have 2, so it can match his buddy helium. And so again, we're really just talking about the non-metals, because we're going to be making covalent bonds. And we see a lot of metals up here. So what you want to do is just look at, I promise I will only use these 11 symbols, these 11 elements as we go through our covalent bonding unit. So let me clear all this and just show you the 11 that we're going to really focus on. Hydrogen, carbon, nitrogen, oxygen, and fluorine, phosphorus, sulfur, chlorine, arsenic, bromine, and iodine. From those 11 elements, we will do the vast majority, all of our covalent bonding work. Okay, we don't really use the noble gases because they're not going to be in our bonds. These are all metals, lots of metals over here that we don't need. Okay, and then silicon, germanium, boron, selenium, tellurium, not very common in bonding, at least at this level, so we're just going to leave them alone. And we'll focus on these 11. Alright, clear that because we'll come back to that in a moment. Alright, so now we're going to look at why this is happening and how we draw these molecules. So first off, let's just take a look at some chlorine atoms. By themselves, chlorine atoms are unstable. Alright, a chlorine atom has 7 valence electrons. It really wants 8 like a noble gas. So 2 chlorine atoms both have an available valence electron to share. And so that's what they do. And 2 chlorine atoms together are very stable, which is why in nature we typically find chlorine as one of our diatomic Hofbrinkel molecules. Alright, and so you can see from this diagram, the chlorine that is green, when you include that shared pair, believes that it has 8 valence electrons. So does the orange chlorine. And so right here is the shared pair, our covalent bond. Now when we draw these, we typically use a dash or a line to represent the shared pair. So right there is our shared pair of electrons, our shared electron pair, which of course we fondly refer to as a covalent bond. Oops, sorry. Sorry, covalent bond. Yes, covalent bond. And this is a single covalent bond because there is just one shared pair of electrons. Again, this is happening because by sharing this pair of electrons, both of the chlorine atoms are more stable. They're in a greater energy position than if they were by themselves. So now let's take a look at the world's most famous covalent molecule, water, H2O. And I want to know how this gets put together. So what I want to do is look at my puzzle pieces. And I just want to put these puzzle pieces together so that we can create this lovely compound. So here I see the Lewis dot diagram for oxygen and for hydrogen. And so when I want to put them together, I see, hey, oxygen has 6 valence electrons. And there are 2 spots for more electrons because oxygen really wants 8. And hydrogen, you see, only has 1 valence electron. And so that's why they go together so well. Hydrogen will share the valence electrons. Whoops, sorry. So I'll move these. Hydrogen will bring its valence electron to share with oxygen. And so there we have water. Now, when we draw this, I want to change those shared pairs into dashes, but I also want to make sure that I keep these electrons on the oxygen, and we'll define those in a second. Now, I just mimicked the puzzle pieces that we had up above, but I could have the hydrogens here and here, or I could have them here and here, or I could have them here and here. It all depends on how you want to draw your molecule. But what you must have is you must have an oxygen with 2 hydrogens attached on 2 different sides, and then you must have these extra electrons still on the oxygen. And again, we'll define those here in a second. Take a moment and try and draw ammonia, NH3. Look at your puzzle pieces, see if you can figure out how to put it together. Pause the video, and we'll check it. All right, so nitrogen, you see, has 5 valence electrons, 3 electrons that it would really like to share. And hydrogen, of course, has the 1. So hopefully you can see that the hydrogens can plug in right there. So when I draw, I'll have my nitrogen, and I need 3 hydrogens with single covalent bonds on 3 different sides, doesn't matter which sides, and then I have to remember to bring over these 2 dots, these 2 valence electrons. All right, and what those dots are and why they're important is because they are called lone pairs. And these lone pairs of electrons might not look that important right now on paper, but we have to remember that these molecules are 3-dimensional. And when we start building them in class and looking at them in more detail, we'll see that these molecules have shapes. And these lone pairs will affect the shape of our molecules, and because of that, also affect their chemical properties and these intermolecular forces that we'll get into in a little bit. And again, those are all single bonds, but there are double and triple bonds out there. Probably the most famous double bond is our oxygen molecule. When we breathe in, oxygen is part of Hofbrinkel, we breathe in O2 because 2 oxygens together way more stable than our separate oxygen atoms. So you can see from our puzzle pieces, our Lewis dot diagrams, oxygen has 6 valence electrons, wants to share 2. So yes, it can form 2 single bonds like it did with hydrogens to make water, but we could also share these 2 pair. And when we do, that's a double bond, 2 shared pair. On paper then, it looks like an equals sign between the 2 oxygens. And again, don't forget our lone pairs. Alright, and so you see that there are 2 shared pair between each oxygen atom. And that makes them happy, stable, because each oxygen, when you include the double bond, believes that it has 8 valence electrons because of the 4 electrons that are involved in that double bond. By the way, when you look at this molecule, this O2 molecule, how many lone pairs are there? And the answer is 4. There's 8 dots, there's 8 electrons, there's 4 on each oxygen, there's 2 pair on each oxygen, but if someone asked you how many lone pairs are on this molecule, 1, 2, 3, 4. Now there's also a triple bond out there, and our most famous triple bond is nitrogen, because again, nitrogen has 5 valence electrons, would love to form 3 bonds to share 3 of those. And yes, just like NH3, we could have done 3 single bonds, but we can also make a triple bond, which is 3 shared pairs of electrons between each nitrogen. Remember the lone pairs. And again, each nitrogen, when you include the 6 electrons in the triple bond, are more stable now because there are 8 valence electrons, quote unquote, around each nitrogen. Of course, when we blend our valence electrons together, we create these molecular orbitals, and this bonding can get much more complex in theory and practice, but for right now, we're good. And by the way, most of our bonds are single bonds. If there's a triple or double bond at this moment in time, I will tell you whether or not there is one. But when you look at our puzzle pieces, and this is the last thing here, you kind of see which elements can form which type of bonds. Okay, again, remember, we're really just looking at hydrogen, these guys, and these guys. So which elements will pretty much only form single bonds? The ones that can only share 1 electron. Hydrogen, and then you see here fluorine, chlorine, bromine, and iodine only have 1 to share. And so those will only form our single bonds right now. Double bonds, well, of course, we just saw O2 because oxygen has 2 available electrons to share. And so when we look at our remaining elements here that we're going to use, they all potentially have 2 valence electrons that they can share. So any of these are capable of forming double bonds. When we come to triple bonds, okay, nitrogen was our example because nitrogen had 3 valence electrons to share. So nitrogen can form a triple, phosphorus can, arsenic can, and so can carbon. But only those ones. And yes, even though carbon has 4 electrons it's looking to share, there is no such thing as a quadruple bond. Alright, I hope this helps with our very beginning ventures into covalent bonds and covalent bond drawing. And I'll see you soon.